Thank you. So first, let me thank the organizers for inviting me to give this talk. And I will talk about joint work with Vera Fischer and Wolfgang Wochowski. Okay, to start, let me recall the definition of distributivity. So a forcing P is lambda distributive if it does not add any new function from lambda to the ordinals. So there is no function from lambda to the ordinals, which is not in the ground model already. And I denote by h of P the least lambda such that P is not lambda distributive. So assume we have lambda is this h of P. This means we have a function from lambda to the ordinals in an extension by P, which is not in the ground model. And now, since lambda is minimal, such that there is such a new function, any restriction to a smaller cardinal than lambda is in the ground model. And this means that f is not just a new function, but it is actually a fresh function. So it's not combined of something else, which is new, but it is new itself, so it's fresh. So now I can define the fresh function spectrum of a forcing. A cardinal lambda is in the fresh function spectrum of P if in some extension by the forcing P, there exists a fresh function on lambda. And now by translating functions from the cardinal lambda to the cofinality of lambda and the other direction, we can see that lambda is in the fresh function spectrum if and only if its cofinality is. So the only interesting cardinals for the fresh functions are the regular cardinals. Because of this, I will talk only about regular cardinals from now on. So we have seen, or yeah, that's by definition, the minimum of the fresh function spectrum is the h of P, the distributivity of P. And as a first easy upper bound, we get the size of the forcing. If lambda is larger than the size of the forcing, then it is not in the fresh function spectrum. Yeah, this follows by a quite easy cardinality argument. So we have the fresh function spectrum is always a subset of the interval h of P up to the cardinality of P. So for example, usual omega cone forcing, it has size omega. So the fresh function spectrum is precisely a singleton omega, as we would expect. We can do a bit better than this size. We can show that if P satisfies that the product with itself as the He CC and lambda is at least He, then this lambda does not belong to the fresh function spectrum. The proof of this theorem is a generalization of a branching lemma. So the lemma says that if we have a tree of height lambda and a forcing such that the product has the He CC, then this forcing does not add new branches to the tree of height lambda. And then, yeah, some generalization gives us that there are no fresh functions on this. So this helps us to get the fresh function spectrum of the forcing which adds many cone reals. So this forcing has no size mu, so we cannot use the first proposition about the size. But yeah, this cone forcing is Knaster, so the product is still CCC. So we get again that only omega is in the fresh function. Okay, do we really need this product thing here, or can we just say that P has the He CC? This is not enough in general, because if there is a Suslin tree and the Suslin tree is CCC, but it adds a fresh function on omega-1. But we can almost do as good. We just lose the he itself here. So we can show that if the forcing has the he CC and lambda is strictly above he, then lambda is not in the fresh function step. The proof of this is based on this lemma by Koelbing about thin trees. If lambda is a regular cardinal and he is strictly less than lambda, and T is a tree of height lambda such that all levels are of size less than he. So there is one fixed bound for the size of the levels below the height of the tree. Then this tree always has a cofinal branch. Or a bit stronger version is that if we assume that the tree is well pruned, then there exists even some gamma below lambda, such that the tree does not split at all above this fixed level gamma. And using this lemma, we can now show the theorem. So assume we have that P forces a fresh function from lambda to the ordinals. Now we consider the tree of possible initial segments of the function f. So if all the sequences such that there exists a condition in P which forces that the sequence is a subset of the function. This is a tree of height lambda and it is well pruned because the function is a fresh function. And so every initial segment of the function is in the ground model, so we can decide it by some condition. So we can decide arbitrarily long initial segments of the function. And the tree has levels of size less than he because the forcing has the he CC. This directly translates into small levels. So by the stronger version here, we get that there is some level gamma such that the tree does not split above level gamma. Now we can take one condition P, which decides the function f at least up to this level gamma. And then since there's no splitting afterwards, this condition P decides the whole function f. And if one condition decides the whole function, the function is in the ground model. So the function is not fresh, a contradiction to the assumption. So the next topic I want to present is the question, which sets of regular cardinals are possible as a fresh function spectrum of some forcing P? And there is a trivial answer. If you allow any forcing, then you can take lottery sums of under GCH Cohen forcings and you can construct any set you want. But if we say we want homogeneous forcings, or we could say that we want that all the fresh functions appear in one extension of the forcing, then the question is more interesting. So I will now talk only about homogeneous forcings. So to start, under GCH, we can take the Cohen forcings for the regular cardinals lambda to get the singletons lambda, because it's less than lambda close and the size is lambda. And then we can also easily combine two of these, taking the product, and then the product is equivalent to first forcing with the larger Cohen forcing and then the smaller Cohen forcing from the ground model. And then using that, any fresh function which has been added by this first one remains a fresh function in the final extension. And using that, both of these forcings don't add fresh functions on omega-2, we can get that here. We get exactly the two cardinals which we put in the product. And then, of course, we can use this for any finite set. What about infinite sets? Here it's more complicated. I call a set of regular cardinals Easton closed if it has the following closure properties. If we have a limit cardinal alpha of A, so alpha is a limit of the cardinals in A, then if alpha is a regular cardinal and not a Malo cardinal, then alpha belongs to A. And if alpha is a singular cardinal, then the successor of alpha belongs to A. And yeah, the Easton closure of a set is, of course, the smallest Easton closed set, which contains A as a subset. And now I use the Easton product of forcings. So this is full support at singular limits and bounded support below regular limits. And then we can show that if we take any set of regular cardinals, then the fresh function spectrum of the Cohen forcing for lambda, where lambda is in the given set A, this is exactly the Easton closure of the given set A. So these closure points here also appear and nothing else appears. So we get that if A itself is Easton closed, then the fresh function spectrum over A is the set A. And in particular, we can realize any Easton closed set as a fresh function spectrum. Why do we need this Easton closure? Well, we cannot avoid it because here's the first example. If we have the first inaccessible alpha and an unbounded subset of regular cardinals below alpha, then the product here adds an alpha Cohen real. Because this is then, in this case, just the bounded support product, and the bounded support product adds an alpha Cohen real, which is a fresh function on alpha. If alpha is Malo, then this is not the case. Then the alpha is not in the fresh function spectrum. And yeah, this is by using the reflection properties of the Malo cardinal. If there would be a fresh function on alpha, then some restriction of this function would be new already, and it's not new because it's a fresh function. So on Malo cardinals, no fresh functions appear if alpha is not in A. And for the singular cardinals, as an example, if we have an unbounded subset of Aleph omega of regular cardinals, then the product adds an Aleph omega plus Cohen real. And this follows from a paper of Schellach, which is based on PCF theory. And in this paper, he shows that the full support product of such Cohen forcings adds a it's any unbounded subset. No.
Oh, you are assuming future.
Yes, so in this paper it is shown that the full support product of the Cohen forcings add a Cohen real on Aleph omega. So we can realize Easton closed sets by Easton products with Cohen forcings. And these products do not collapse cardinals. If we allow, okay, first, therefore we conjecture that if P does not collapse cardinals, then its fresh function spectrum is always Easton closed. If we allow the forcing to collapse cardinals, then we can do a bit more. We can get sets which are not Easton closed. So first, if P collapses some cardinal lambda to the distributivity of P, then this cardinal belongs to the fresh function spectrum. So all the regular cardinals below, between the distributivity and this lambda belong to the fresh function spectrum because they all get collapsed, right? So, for example, under CH, the collapse, which collapses omega 2 to omega 1, as the fresh function spectrum omega 1, omega 2. So we can get here this set of all the aleph n's by using the collapse, which collapses aleph omega to aleph 0. And this set is not Easton closed because, yeah, aleph omega plus 1 would be in the Easton closure. And we can also get for singular Xi or for inaccessible Xi, we can get these intervals from mu up to Xi by using either the collapse or the Levy collapse. And again, these sets are not Easton closed. So some questions. We do not know if we can get a strict subset of the aleph n's, which is infinite. We can get all of them by collapsing, but we cannot avoid any of them. And also if we have an inaccessible cardinal Xi, which is not Malo, and we have an unbounded, co-unbounded set of regular cardinals, we don't know if we can get this set A. So this was about what can we realize? And now the question is there some set which cannot be realized, at least consistently? So let's start with simple or with easy sets. So the singleton set omega is always the fresh function spectrum of Cohen forcing. The singleton set omega 1 is under CH, it is the fresh function spectrum of the omega 1 Cohen forcing. And if there exists a Suslin tree, then it's the fresh function spectrum of the Suslin tree. But is there always such a forcing in ZFC? To answer this, we use Todorcevich's Maximality Principle, which says that if P is a forcing which adds a fresh subset of omega 1, then P either collapses omega 1 or omega 2. And here a fresh subset, if we want to translate the fresh subset to a fresh function, that's a fresh function from omega 1 to 2, and not arbitrary to the ordinals. This principle is consistent relative to an inaccessible cardinal. And we can show that if this principle holds and zero sharp does not exist, then any forcing which has omega 1 in the fresh function spectrum has also omega in the fresh function spectrum or omega 2 in the fresh function. So here the zero sharp does not exist is necessary because we want to use Jensen covering lemma to translate the fresh function on omega 1 to a fresh subset of omega 1. And then we can apply this principle. So under this assumptions, the singleton set omega 1 is not realizable as a fresh function spectrum. So yeah, that's so far the only example of a set which is consistently not realizable, which we have. So now I want to show what the fresh function spectrum of free forcings on omega are. So first, the CCC forcings, such as Cohen forcing, random forcing, and Hechler forcing, they are cluster. So the product of the forcing with itself is CCC, and therefore we can use the first proposition to get that singleton omega 1 is the fresh function spectrum. What about the other non-CCC tree forcings? We know that omega is always in there because they all add reals, and the spectrum is bounded by continuum because of the size of the forcing. Now we can show that for any Miller-like tree forcing on lambda to the less than omega, and if delta is larger than lambda to the less than omega, then this delta does not belong to the fresh function. What is a Miller-like tree forcing? So it is above every node there is a splitting node. If we take a condition in the forcing and a node, and we restrict the condition to this node, then it is again a condition. And this third point is a bit more complicated. So if we take the stem of the tree, and for every successor of the stem, we take the restriction to this node, and we take some stronger condition than the restriction. So we can thin out every part of the tree above the stem. And then we take the union of all these restrictions, then we get again a condition. And the forcing has the fusion property. These are Miller-like tree forcings. And now it's easy to check for all these forcings that they are Miller-like. So we get that Miller forcing with respect to an ideal, Sachs forcing, and full Miller forcing all have singleton omega 1 as the fresh function spectrum. And we also get that number forcing, the fresh function spectrum, is a subset of omega 1 and omega 2. Because number forcing is a Miller-like tree forcing with omega 2 here. What about Laver forcing? Laver forcing is not Miller-like because there you always have to split after your first splitting. So you are not allowed to have a non-splitting node above the stem. Here the Y properness helps us. So David and Yindra showed that Laver forcing is Y proper and that uncountable cardinals do not belong to the fresh function spectra of Y proper forcings. So we get that Laver forcing has also singleton omega as fresh function spectrum. Now let's look again at number forcing. Number forcing has the fresh function spectrum omega 1, omega 2. So because it's Miller-like, we knew already that nothing above here is in the fresh function spectrum, but it is actually equal to this set. And then here it's interesting that number forcing, for number forcing, the fresh subsets and the fresh functions are not the same. So yeah, it's well known that there are no new subsets of ordinals smaller than omega 2. And yes, so number forcing adds a fresh subset to an ordinal alpha, if and only if alpha is at least omega 2, and the cofinality of the ordinal is one of these three cardinals. And similar for Prikry forcing. For a measurable cardinal kappa, we have the fresh function spectrum is omega and kappa. And again, fresh subsets are added for an ordinal if and only if it's at least kappa and the cofinality is either omega or kappa. So as a last thing, I want to discuss the fresh function spectrum of Mathias forcing and silver forcing. As a preparation, I need the fresh function spectrum of P omega mod finite. P omega mod finite collapses the continuum to H, which is the distributivity of it, which, yeah, this is the base matrix theorem. And then, since cardinals which are collapsed to the distributivity are in the fresh function spectrum, we get here all regular cardinals between H and C are in the fresh function spectrum. And now we can use that Mathias forcing is equivalent to first forcing with P omega mod finite and then Mathias forcing with respect to a filter. So this forcing here gives this interval in the fresh function spectrum. And since the Mathias forcing with filter is sigma centered, no cardinals between omega and H come here into the fresh function spectrum. And of course, omega is in there because reals are added. And yeah, similarly for silver forcing, again, it is equivalent to the omega mod finite followed by Grigoriev forcing with respect to a filter. So we get again the interval and omega, but here we don't know if anything in between is also in the fresh function spectrum. Yeah, because we don't know if Grigoriev forcing adds something above omega to the fresh function spectrum. So these two are examples of tree forcings which have more in the fresh function spectrum than just omega. So there are many tree forcings have just omega, but some tree forcings have also more cardinals. Okay, thank you. That's all I wanted to say.